So my name's Jed Sundwall, and I run the Open Data program at AWS. And one of the first things I like to get out of the way when talking about the Open Data program is answer why we have an Open Data program. And the short answer to this question is that open data is really important to a lot of our customers. We have, in the public sector, as you may have heard, we have tens of thousands of customers around the world. And many of these customers are required by law or by their mission to share data, to make data open and available. And then on the other side of this, we have millions of customers all over the world. And many of them rely on access to data to build their products and services. They might provide some sort of data product or some sort of software application that analyzes and makes sense of open data that governments have shared. And the cloud has a lot to offer when it comes to not only providing all the storage infrastructure to host that data and make it available, but also to analyze it on the other end. And what we do in our program and what our mission is to expand access to data. That's the main thing, is that what we try to do is create a world in which more people have access to data every day. We're trying to make sure that people who didn't have access to data yesterday might have better access to that data today. And the way that we do that is by finding ways to stage data for analysis in the cloud. And if you go to our site, we've got a nice site. I think it's a nice site. opendata.aws. You can see some examples of what our customers are doing today to make data easier to access by making it available in the cloud. One of the ways that we do this, do our work, is through the Public Dataset program. It's called the AWS Public Dataset program. And in this program, we actually collaborate with a lot of our customers to figure out new ways to stage data for analysis in the cloud. And now's probably a good chance for me to explain why I keep using this very specific phrase, stage data for analysis in the cloud. It's very easy to look at AWS or the cloud, and if you're familiar with Amazon S3, our storage service, and think of it a lot like an FTP server. It's like, wow, that's like the best FTP server I could ever imagine. That is true. It does act a lot like an FTP server. But the real value of making data available in the cloud is that it allows you to work with the data, and S3 in particular provides a lot of affordances for you to work with data without moving it around very much. So that you can very precisely query or interrogate data in massive amounts of data without moving it around. And this has a huge impact on research in terms of saving time, and cost savings. Because it means that people can work with large volumes of data without having to download or copy those volumes of data. And so what we do is we work with these customers who have large and interesting data sets, and we try to figure out what is the best way to stage this data for analysis in the cloud. And that's basically the thrust of what we're going to talk about today. And when my colleague Dave Rocamora comes up, he's going to talk in much more detail about what we've learned from doing this. You can find right now, if you go to registry.opendata.aws, I think last I checked, it was 59 data sets. We keep adding them. New ones keep coming up all the time. We just added a new one from the Allen Brain Institute. But there are about 59 data sets there that cover a wide variety of topic areas and domains. And anyway, you can find data that you can work with right now at registry.opendata.aws. And another nice thing about this site is that for each data set that we have listed there, we usually have usage examples. So it's what we call the data at work section. So the data's there in the cloud, and then you can also see examples of what people are doing with the data, how they're using it, and a lot of those examples include tutorials that can actually teach you how to use some of our services to learn how to use the data. And I'll give a special shout out to another new data set that that was just added to the registry, which is the Hubble Space Telescope data. So we have a lot of data from the Hubble Space Telescope, and the Space Telescope Science Institute, hope I got that right, they went through the trouble of creating a really cool tutorial that shows off how to use AWS Lambda to work with that data. So not only do you have access to some really phenomenal data from the Hubble Space Telescope, you also have a nice tutorial that can introduce you to using Lambda if you've been interested in experimenting with that. So what I was saying before about this notion of staging data for analysis, there's this quote that we like from a book called Data Driven by DJ Patil and Hilary Mason. So DJ Patil used to be the chief data scientist of the United States. And he and Hilary Mason wrote this book called Data Driven. It's more like I think maybe like a pamphlet. Like it's not a very big book. You could read it on a cross-country flight, I think, pretty easily. And last I checked, it was free on the Kindle. It's a really nice book explaining how to, some of the things you can do to create a more data-driven culture within your organization. But one thing I really like about this book is that they finally wrote down this 80% figure, this idea that 80% of a data scientist's time is spent just preparing data for analysis. We hear that all the time. I'm seeing heads nod here. The really great thing about this book, though, is they wrote it down, so it doesn't sound like I just made it up. I think, I'm sure no one's actually done real rigorous research on this, but everyone tends to agree that it's at least 80%. And this is a serious problem. In many cases, especially these days, data scientists are in demand. There aren't that many of them. There's a very competitive market for them. So you probably pay them a good amount of money. You don't want them spending most of their time just preparing data for analysis or just downloading data. You want to get them to get to work on the analysis and do what they're good at. And it can be very frustrating, I guess, is what I'll say. We've worked with a lot of researchers, and we've talked to a lot of our customers who they've wanted access, or they've had ideas of cool things they could do with data sets, but just getting the data is blocking them. They either don't have the storage capacity themselves, they can't afford it themselves. If they went and asked IT for 100 terabytes of storage capacity, they would get laughed at, and they don't want to be embarrassed. So they just say, you know what, I'm just not going to bother with this question. Like, I have an idea of what I can do with this data, but getting the data in the first place is just, I can't figure out how to do it, or it'd be too painful, so I'm just going to think of something else to do. And we hear this all the time, and we hear this from a lot of, from customers that even have a fair amount of money. It's not like the budget is really the issue. In a lot of cases, it's just the time. And so I'll just say, this breaks our hearts. We don't want this to happen. We want people who have questions that they'd like to ask. We'd like them to be able to ask those questions. And we have a term for this at AWS, or actually at Amazon. We use this all throughout Amazon, this idea of undifferentiated heavy lifting. Undifferentiated heavy lifting is all the work that you or your team has to do that is keeping them from doing, or keeping you from doing what you actually want to do, from what your actual mission is or what you're actually good at. And everything that we do at AWS is designed to attack undifferentiated heavy lifting. We're always trying to work with our customers, listen to them, find out what it is that they have to do that's keeping them from doing what they're good at and what differentiates them and what's going to distinguish them from their competition or help them accomplish their mission. And it's easy to see this in the context of the infrastructure that we provide. It's really nice that you can get a server with fully configured server for whatever you need without needing to order it and wait for it to arrive and unbox it and plug it in and screw it into a rack, et cetera, et cetera. You don't have to do any of that stuff. You can just get to work if you have an idea. The same thing applies to data, and that's what we're trying to do with the Public Datasets program and with the Open Data program generally, is make sure that people understand that the cloud really allows researchers to eliminate a lot of undifferentiated heavy lifting and get to work with data very quickly and very cost effectively. And this is the way it works, well, visually. I've sort of been hinting at this, but what data acquisition in the cloud, basically there is no acquisition, right? Instead of taking the data down to wherever you're gonna work with it, you bring whatever compute resources you want close to the data. You just deploy them close to the data in the cloud and get your work done. And the advantages that come from this, there are a few that we've identified that are very clear. But one that might not be as obvious because it's not an obvious sort of like technical solution or an AWS product is just our users, our community of users. Like I said before, the Space Science, the Space Telescope Science Institute, they know how to use AWS, and they went through the trouble because they want people to use their data, or they want people to use the Hubble data. They went through the trouble of creating a tutorial that teaches people how to use Lambda. We have so many users using AWS that there's an abundance of support out there in case you're trying to get started with something or if you want to figure out ways to work with data in the cloud. The answers are out there, if on Stack Overflow or people's blogs and tutorials that exist all over the place. It's a huge asset. So when data's up and available in the cloud, you've got a huge community of users that can help you figure out how to do stuff with it and that are sharing tips and tricks with one another to do it. And then additionally, some things that we've seen through the Public Datasets program is that when we make a really large and interesting data set available, it gives this community of users, or various communities of users, an incentive to start building tools to work with that data in place. And we've seen some really remarkable collaborations start happening, specifically around meteorological data, satellite imagery, and then also in the past few years, a bunch of data that we host with IRS. It's nonprofit tax filing data. And little communities have emerged around these data sets because they can all work on one data set together and figure out together interesting ways to work with the data and extract value from it. The other thing is that we're always adding new services and tools. So I've mentioned already a couple times AWS Lambda. That didn't exist 4 years ago. Or maybe it did. I don't think it existed 4 years ago. Yeah, I've been here 4 years. It didn't exist when I started at Amazon. So something like Lambda comes out, and it completely changes the game in terms of how people think about approaching data. And this is happening continuously. We're very aggressive about adding new services and tools. And a data set that existed on AWS before and after Lambda has sort of different value, right? Before it was awesome, and then after Lambda it's like even awesomer. It's great because you have another option, another way to work with it. And then these last two benefits that we have here, they're kind of the same thing, right? If you assume that time is money, you can do research much more quickly. You can ask questions much more quickly. The cost of asking a question is greatly reduced. And that means the cost of research is greatly reduced. And we're always really gratified when we're able to hear from people who have been able to even start a company or do a research project that they just never thought would have been possible before because they couldn't get the data because it was too expensive either in terms of the infrastructure cost for them or just the time. And so that's why we do what we do. That's why we believe that staging data for analysis in the cloud has real benefits for users. And on that note, I'm going to hand it off to my colleague Dave, and he's going to talk to you in a little bit more detail about what we've learned about staging data for analysis in the cloud. Thanks.
Thanks, man.
Good luck.
All right. Thanks, Jed. Hey, everybody. I'm Dave Rocamora. I'm a solutions architect. You guys were not kidding about the lights. I cannot see anything out here. So this is going to be real easy. Hopefully I don't fall off the stage. So I'm a solutions architect at AWS. I work with Jed because I was riding the bus with him to work, and he just got me obsessed with this idea about data and sharing data, and I drank the Kool-Aid, and I'm on board. So I work with our customers that are putting data into AWS in the Public Datasets program and people that are consuming it to help them out technically to make sure that they're getting the most value out of what we're doing in the program. And of the 50 data sets that are in the program right now, it'd be great to say that every one of them is a blowout success and customers access them like crazy. The way that we measure success for our program is how much that data is accessed, how much is used, are people building examples and tutorials and basing things off of it. The truth is, though, is that not every one of the data sets is a wildly successful thing where people are using it all of the time. But that's OK, and we've used this as a sort of a lab to understand what's working well and what doesn't work. And so in my section here, I'm going to talk about some of the patterns that we see that make the biggest difference for making a data set a real successful thing where lots of customers use it and where they don't. And the thing about this that we found through putting it together is this is based on the 10 petabytes of data that we have in the Open Data program, or the Public Datasets program. But the truth is that the ideas and the techniques matter for any volume of data, and they matter for data that's not necessarily even public. So I do a lot of time talking to customers that are sharing data, or putting together data for an internal project or a product that they're building, or to share with a federation of users at their company or other companies. It doesn't necessarily have to be all open data. So there's stuff that you can learn about this that even if you're not doing open data, that's relevant. So the first thing the first and the biggest thing, and this is not actually really a technical thing exactly, but a lot of the other things that you can do derive from this, is that for a data set to be really successful, it needs to be treated like a product. For anybody that's worked with open source software, there's kind of an idea around that, or some people think, OK, you just put it up there and people will start using it. And it's the same with data. When I tell people, even at Amazon, what I do, they say, well, that's easy. You just upload the data to S3, right, and you're done. Yeah, not exactly, right? So data sets that are really successful are treated like a product. And so what does that really mean, right? So that means that, first off, you're thinking about your customers that are going to use the data set. Think about the tools they're going to use to access it, the kinds of questions they're going to ask of it, sort of what they're going to have to go through to get involved with your data. And that usually means that'll inform how you make that data available and how you prepare it. That also informs like how you document your data set, which becomes really important. Documentation, providing examples like Jeb was saying, providing a way to get feedback and support, and ask questions to the people that are maintaining the data set. I mean, really, for us, this is the biggest deal. This is the biggest thing that separates a data set that gets used a lot and ones that don't. So this is, if you've been to the registry, which Jed mentioned this, and if you've been to other sessions, you might have seen this thing. The registry of open data is, on AWS is where we list the data sets. And it's funny because it's a pretty simple idea, really. It's just it's a kind of a form that has a bunch of required fields in it, right? But this is sort of what we think is the minimum for like a product to have to do to be a good data set in our program. So you have to have a description of what you're doing, describe the license, how often it's updated, who to contact to use it, and some examples, well, I guess where to get it, and some examples about how to use it. So in my discussions with customers in the open data world, this makes a ton of sense because you want people to use your data set. But even internally, for customers that are building like a data lake, for example, for use within their own organization, a lot of this stuff is really relevant, especially this examples thing. Just putting data out there without showing people how to use it, in our experience, we found that people are less likely to use that. I mean, it's sort of obvious, right? But it was cool to see that really come true with this thing. This data set in particular is called the Common Crawl. It's a once monthly crawl of the internet, and it's very popular for machine learning and natural language processing. But you can see this in other data sets there, and the registry is not like the perfect solution for describing how to use a data set, but it shows sort of the kinds of things that product owners that are considering their data set are putting up there. So please steal ideas from the registry about how to organize data that's in your organization. So the next thing that becomes really important, and this is really derived from the first one, and Jed was talking about this, about how you can use S3 as a giant FTP server, but it's not ideal. The data set is optimized for the cloud. And this is really related to treating data set like a product, because we found that the people that treat their data set like a product and consider their customers are considering how their customers are going to use the data set. And when it's in the cloud, and it's large, customers tend to be using the cloud to access it. And so optimizing that data set for the cloud becomes really important. And I can go through, that's a pretty like hand-wavy term, optimizing for the cloud. So I'll go into that in a little detail. So take a look at this imaginary graph. So when I talk to customers that are hosting data sets for the public data set program, or to work with in a data lake or something like that in their own organization, there's usually, people come to me from two different extremes, okay? First they'll say, all right, we have this data set that we produce through an internal process. We're mandated to provide it, or I don't have the staff to do any preparation on it or anything. I have a backup from this system. This is an internal tool that we use, and this is the data set that makes up that internal tool. Just let's upload the raw data to S3, and we'll let people go at it. They'll figure it out, right? From experience, that's not true. People don't necessarily figure it out. We found that data that's not really prepared well for analysis doesn't get used as often. And it's really like, when I say raw data, a good example of this is like a database backup, like a MySQL dump, or a bunch of tarballs that are like a backup of another system, or when you have data that's in a very proprietary or specific format for one kind of application. If customers have to take that raw data and do something to it to get started on their next thing, and if you look at that and you think, well, every customer is going to have to extract this tarball, for example, then you're dealing with this raw data that becomes a little bit less useful for customers in the cloud. So on the other side of this equation, or equation, graph, spectrum thing, people come to me and say, all right, well, we know exactly here's the 10 things that our customers are going to do with our data set, and so we want to build this beautiful experience with them through an API that they can use to access and work with the data. And so they end up building, or they propose, or maybe they do end up building an API that extracts just the forecast for certain cities from a weather model or something like that. So we found that this also, maybe paradoxically, limits the usage of the data set. And it's kind of challenging too. It has some problems. So the first challenge here is that building an API is building software. and maintaining software. And that means considering and understanding how every single thing that your customers are going to use your data set for. And customers are sometimes hard to predict like that. That also puts a lot of maintenance on you to build and maintain that software. And it's not just the software, right? It's not just the API that serves up your data set. It's all the clients. So if your customers are programming in one specific language or using some tool, like a science tool or using an AWS tool like Elastic MapReduce or something like that, they'll have to incorporate your client into that. And that's a lot of work. It's a lot of maintenance. And it's hard to keep up with. So we find that those kinds of data sets aren't really widely used. What we believe in is the thing in the middle, which is not labeled, which is something that's beyond raw, but not highly processed. So taking data and sort of preparing it to a point where it's ready to be analyzed, things are extracted. All of the first steps that anyone's going to have to do with this data set has been done for them. It makes a huge difference. And it makes the data much more likely to be used and much more usable. Now, critics would say, I was talking about APIs here, and critics would say, well, Dave, you're talking about putting data in S3. S3 is an API, and that's true. So S3 is an API, but the difference between S3 as an API and building your own is that S3 has been around for 10 years, or over 10 years. And AWS builds and supports all of the SDKs for S3. And a lot of the tools that you and your customers are already using probably already have support for S3, or they may already have support for S3. So we think this middle route, preparing and organizing the data in S3 provides the most likely scenario where your data gets used. And a little bit more about how we can organize that data in S3. This becomes, I'm going to go through some pictures here, becomes really relevant to all data sets. And I think a lot of the meat of my work is talking to customers about this very thing. So to make your data set really successful and really useful in S3, what you want to do is minimize the amount of data that has to be copied or transferred. This becomes obvious. Jeb was talking about the speed of research and the cost of doing research. The big cost for working with large amounts of data is involved in transferring it and computing it. So if it takes a long time, if you're transferring a lot of data, it's going to take a long time to do that. If you have to compute it, you're going to have to run computers. These things take time and money. So let's imagine that we have this data set that's made up of these gray squares, and they could represent anything from gigabytes or megabytes or gene sequences or satellite imagery scenes or something like that. With some traditional methods, if you only wanted to get a couple of these blue boxes out of the big, massive gray boxes, if the data set's not prepared well, if it's in a raw format, like a backup, or if it's in something where it needs to be processed to be usable, or the data is locked away inside of a compressed archive, like a zip file or a tarball or something like that, customers are going to need to download a lot more data than is required. I mean, this is probably your worst case scenario when to access 10 megabytes of data, you have to download a terabyte, But believe me, it happens. And so this is something that you want to avoid. We find that data sets that are organized like this, where customers have to access a significant amount of data to get the bytes that they actually need out of there, people are less likely to use it because it becomes expensive to operate. Here's your ideal scenario, or very close to ideal, is if you can sort of organize the bytes that you're storing in S3, or storing in the cloud system that you're using, in a way that allows the customer to extract just the bytes that they're looking for. And maybe there might be a little bit of waste, but if we can minimize the amount of wasted bytes that they transfer and compute, we can save them a lot of money, we can speed up their analysis, and a lot more people will use the data set. The kind of bummer about this is that every data set and every data is different, but actually that makes my job really exciting because I get to find out different ways to do this. So for a real tangible example of this, so Landsat on AWS is one of the, it's probably 4 or 5 years old now on our platform. Landsat's a satellite that takes images of the Earth. It's from the USGS. The way that Landsat imagery is historically distributed is that Landsat cruises over the Earth and takes a scene, and a scene is it's a pretty large geographic area. And Landsat has, I believe, 12 different wavelengths of light that it can collect. And so the way that USGS was distributing the data was that you would have a tarball, which is an archive, a compressed archive, that included all 12 of the images and a bunch of other kind of data in there, and it was all packed up. And for a customer to use that, what they would have to do is download the entire archive, which was a couple hundred megabytes, and then extract all the objects out of there, or all the files out of there, and then begin to do their analysis. So in talking to customers that use Landsat data, it became clear that a couple things were happening. First, most customers didn't need every single wavelength. They didn't need all of the different bands. They only needed 1, 2, or 3, something like that. The other thing that happened is that people are not always interested in the entire Landsat scene. They want sort of a subset of that. So when Landsat on AWS was made available, we do a pre-processing step where we first extract all of the objects from the tarball, so you no longer have to download the entire thing anymore. And then we reorder the bytes inside of the image into a format called cloud-optimized geotiff. And that does a thing called internal tiling, which, long story short, it allows you to select, I mean, it probably has a ton of features that I don't understand, to be honest. But one of the things it allows you to do is to select a byte range of an object and get just the pixels that are in that area. So instead of getting, like I live in Seattle, instead of downloading like a Landsat scene of like the entire Puget Sound, I can just get the area around my neighborhood. So really a dramatic reduction in the amount of bytes transferred to do meaningful work with the data set. And sort of to quantify this, if I can, there. This is from Drew Bollinger at Development Seed. Follow him on Twitter. He told me to say that last night. Or he told me not to say that last night, but anyway. So they had a pipeline that was processing Landsat scenes. And the vertical axis here is the amount of time it was taking, the latency to get a new Landsat scene and put it into their system. And they had this kind of dramatic reduction in the amount of time that it took. And the difference is this is actually kind of, the difference here is that before they were having to download the entire object, so they were spending some time, the computer was hanging out while 600 megabytes or a couple hundred megabytes was being transferred into the computer and then extracted. And then they would just get the bits that they wanted out of there. The big shift just came from being able to download one wavelength at a time, or just the wavelengths they were interested in. This graph is actually before they made further optimizations to use the parts of cloud-optimized geotiff that could extract smaller subsets. So, I mean, it makes a huge difference in the amount of time that it takes to process things. And it's a big deal for these data sets. You can get away with a lot of things when you're dealing with a smaller amount of data. If it's like only a couple gigabytes or a couple hundred gigabytes, maybe it's OK. But as you get bigger and bigger, this becomes a real problem that needs to be addressed. And we find that going after it early makes a lot of sense and makes the data set really successful on our platform. So if you think about the things that I described with Landsat and the problem in general, how do we get just the bytes you need from the gigabytes or petabytes that you have, right? We're talking about building like a map or an index of the data set, okay? So that you can find just the bytes that you're interested in. The cloud-optimized geotiff and the way that Landsat scenes are organized on Landsat on AWS, that's an example of an internal index. So in the objects, in the files, they have a map at the beginning that says, these bytes represent this geographic location. And intelligent software can read that and make sense of that. There's other examples of internal index in different file formats. If you've heard of Apache Parquet or Apache ORC, they're formats for columnar data, for tabular data, and it organizes them into columns, and it has indexes that allow you to just do range selects of different parts of it. The Common Crawl actually does a good job of, they have their own file format called Work, and combined with an index that they also now store in Parquet, you can do this kind of extraction, which is pretty cool. The internal indexing is a good option for a lot of things. But there's other patterns we see that are super common. The first one would be like key index, and the next one's an external index, and I'll talk about each one of those. So a key index is, it's pretty obvious because you probably already do this. If you use a computer right now, you organize files by different file names, okay, right? S3, if you haven't used it, it's a big key value store. So you have objects that have names. And we find with most of our data sets, what our customers will do is that they'll organize the keys in the data set, just like you would organize files and folders on your computer. This is an example from Go16, which is a NOAA satellite that we're storing the data for in the program. It has a very long key name that wouldn't fit on one line in the slide and still be readable, so I sort of split it up. But one of the interesting things about the way that they've organized this data is that the key name has a lot of information encoded in it. And I can't actually read my notes to tell you what they are, but it has the date and the time, the sensor, the modality, a bunch of other information about the image that was taken. And this is a pretty successful strategy with a lot of our data sets, is to have key naming and key naming that's predictable. And so we've seen, like with the radar data that Jeb was talking about, we host the NOAA NextRad data. There are customers that use that data set, and the key naming is really precise about what it is and what the object represents. And it can be sort of constructed ahead of time. We've seen customers that are building software that know before we really know that we've put the data, you know what I mean? Like that they can start accessing it. We've seen that happen. So having a predictable key naming scheme And encoding information in the key name makes a big difference to making that data accessible. And it's a pretty straightforward thing to do. Like I said, you probably already do that. Another example of an indexing technique that's really successful in allowing people to get just the bytes they need out of the petabytes that you have is using an external index. So in the IRS 990 data set that Jed mentioned, if you were to go to that S3 bucket and open up, it's actually like 11 million XML files that have a pretty opaque name. And they're all in like a big flat organization. So let's say if I was using that data set and I wanted to get information on a very specific nonprofit or nonprofits of a certain size or configuration or something like that, getting through that data set would be pretty challenging. I'd have to access 11 million objects maybe to do it. So what they do is they provide an external index. And I mean, this is a pretty simple thing. It's really just a CSV file in there. And the CSV file has extra information. So it says, here's some of the fields that are in there. And it sort of points you to the right data. The external index can get a lot more sophisticated. I know that Synergize in the room runs an external index that's like a service that sits next to the data set. This is the Sentinel-2 data set that they host, so it allows you to access or understand where other data is inside of there. Common Crawl uses an external index that includes a lot of metadata in there, and it's in a format, it's in Parquet, so you can query it to be able to understand where your data is. But providing that kind of capability is really important. So all these things, the internal index, the external index, the key naming thing, are all strategies for making data more accessible by allowing your customers to transfer fewer bytes to get their information out. And a lot of data sets will actually use a combination or all three. Like Landsat actually uses all three, and it's a pretty good way to do that. So those are just some ideas about what we've seen that's successful there. So the last thing that we find that makes data sets really successful and popular and accessed is the fact that there's a community around it. And typically we see the product owner of a data set driving a community. Like I was saying earlier with open source software, there's an idea like if you just threw the software up there, people would start contributing it, using it, and giving you back bug reports and stuff like that. And it doesn't always happen. There's some work that goes into building a community, and it's the same thing with the data sets. And so it's interesting. So we'll revisit that imaginary graph from before, but look at it in a little different way. This is what we've seen happen with our data sets that are prepared well and that have someone that's managing the community or a group of people that are interested parties that are sort of building onto the community. If the data set provider can prepare the data well enough, make it organized and ready for their customers to use it, document it, provide a place to get feedback and commentary and have discussions about the data set, and share examples of what they're building, if they can get it that far, then the community can take it further. And this sort of helps overcome some of the challenges that I was talking about earlier around highly refined data sets and building APIs, because the community can start building those things for you. And so in the open data world, that means people like jumping onto the data set and building derivative data set products, or derivative data sets, or derivative services that are based on the data set that broaden the level of access to allow more people to get involved with the data set. Someone that's maybe like a non-traditional user access it through a very easy-to-use website, or annotate a data set to make it useful for a very specific audience. The community sort of takes that on and builds it and runs with it. We've seen a lot with our successful data sets. We've seen this happen a lot. An example is the community that's around Landsat on AWS and around cloud-optimized geotiff in general. By providing this, like a petabyte of cloud-optimized geotiff data, it's sort of created this sort of ecosystem of vendors and tool builders and users that were working with cloud-optimized geotiff and building a lot of pretty amazing products off of Landsat. One example of this is Mapbox made this landsat-tiler. This is cool because it's the animated image in our presentation. But what this is doing is, so the Landsat on AWS product is just those geotiffs that are organized in S3. And what this tiler is doing is it uses Lambda to generate tiles in real time as someone's browsing around or requesting them. So it's like a tiling server. That's a serverless tiling server, I guess. And this is a pretty neat thing. It's not part of the Landsat data set, but it uses the Landsat data set, and it's sort of an extension of that to make it much more usable and to open it up to other people. And also just, because it's a serverless thing, it's really interesting. If you're not using it, it doesn't, run any compute. And it can sort of scale dynamically to support the number of users that are using it. So it's this kind of innovation that's possible by building a good product, a data set as a good product, and working with the community to sort of expand its usefulness. So those are the three things that we think are the biggest factors in making a data set successful, whether it be an open data set that's public or something that's used internal. So treating a data set like a product, so having a product owner, thinking about your customers that are using it, building documentation and examples, optimizing the data set for the cloud to make sure that the way your customers use it can be efficient, reduce the number of bytes they have to transfer, reduce the amount of prep work they have to do before they get started. And then finally, organize and build a community around it, whether that be a public community or an internal community that's working with your data, to sort of build derivative products and other tooling that's based on the data set. And please, okay. All right, well, that was sort of a, but okay. Please complete your session survey. I think there's supposed to be a thank you slide there, too. Okay, yeah. Well, yeah, so thank you very much for coming. I know you had a lot of choices today, and I hope this was useful. I think Jed and I can answer questions for a couple minutes, but if you do have any think of questions afterwards, feel free to send either one of us an email. Thank you.
Any questions? We'll bring the mic to you if you have a question. Right here.
And I can't see anything, so.
Hello. Tim Loomis here.
Oh, hey, okay, I see you.
I can't let cloud optimized GeoTIFF go without getting a little bit more explanation, because optimize to me means compress or subsets. What do you got going on there?
Okay, I mean, I can try to answer this question.
I take it, I think. So the main thing that happens with the cloud optimized GeoTIFF is the pixels, the binary data in the TIFF are basically, it's rearranged. So the scientific value of each pixel is not changed. But typically, well, like if you ingest a TIFF or start opening up a TIFF, the binary data goes row by row. So it's pixel by pixel, left to right. What they do is they rearrange the pixels so that the first pixels you get would actually comprise a tile within it. And then what's in the header explains, it says this TIFF is this big, and it's, I don't remember what the number is, but it's like in 64 pixel square tiles.
Yeah.
Based on that, you can, if you have an understanding of where it is in the world that you're looking at, you're like, you know what, I want to look at this one patch of rainforest. Give me from this byte range to, from these bytes to these bytes, and it'll just give you a tile.
Yeah. And then also, I mean, the information that's in that header isn't just like pixels and bytes. It's like geographic information, like coordinates and stuff like that. So
yeah, it gives you the coordinates.
Does that make it a little more clear?
Sure.
Yeah. Sure.
So
okay.
It lets you retrieve very precisely, and then you can have compression. I think it uses deflate compression within the TIFF. So the TIFF is compressed. I mean, the data is compressed.
So I work with the Go16 data in the net-CDF file.
Yeah.
A huge array
Yeah.
of values. You guys really, would you rather have a GeoTIFF?
Some people would.
Well, yeah. I mean, so NetCDF is, NetCDF has similar capabilities to like what cloud optimized GeoTIFF is. I would say, when it comes to finding that optimal format, there's the efficiency and making it efficient to access it, but there's also tooling support.
Right.
If people are used to consuming Go16 data in NetCDF, converting it to cloud optimized GeoTIFF might mean that, well, a lot of the tools that your customers already use just won't work. And so that might not be a good fit. So it's about finding a compromise. Love to talk to you more about how we can make Go16 data even better than it is.
There are a lot of groups working on HDF data, figuring out how to cloud optimize HDF data, like NetCDF.
Yeah, hi. Thanks for your discussion. And we've been talking a lot at NOAA about whether to optimize, how much to optimize on the way in, so that's great. I'm just wondering whether there's one other thing that can be done to help with data discovery, or whether this is just BS and it wouldn't work. I think when you put in an S3 object, you can create some custom metadata fields. Is it useful to do that, to add things like, start time of the scene, end time of the scene, bounding box, other attributes, sort of geospatial attributes? Mm-hmm. And is there a way to then say, okay, just go and find me all the S3 objects, in this bucket or set of buckets that have some of those custom metadata fields? Is that helpful? Can you do that? Are there sort of built-in tools that would let you make use of that at all?
Yeah, well, that's a great question. So with S3, you have the key name, and then you have the data that's in the object, and then you can also have these extra metadata fields. And then recently, there's support for tagging objects in S3. So you could pack extra information in there. The challenge is like the ways that S3 makes that visible to you. So for example, the list API, so we're talking about those custom metadata fields on objects. The list API right now doesn't return those and it might not return those. I don't know what the plan is there. So you wouldn't be able to say, oh, show me all of the images that were like this. For that, we're seeing customers use the external index kind of technique. I would say that when it comes to that key naming thing, there's definitely a limit to the amount of information you could pack in there before it becomes like not so useful. I mean, kind of the bad thing about the advice I give is it's always like, well, it kind of depends. There's something in the middle. But I would say right now I'm seeing customers successful with packing that extra information into an external index.
Yeah, that's fine.
The example of how the Common Crawl does it, I think, is really neat. They had their own index format that described in more detail what was inside of their objects. And then they recently moved or made a copy of that in Parquet. And so customers are creating an Athena table, which is like this database engine thing we have. And without having to do a lot of work or set up any custom software, they can see exactly where their stuff is. And that might be an option.
And just to add on to that, one of the cool things about what Common Crawl did is, I mean, their index is huge, right? They have like so many objects that they have to index. And so having that metadata index in Parquet really makes it approachable for a lot of people. You know, before it's like, all right, I got to figure out what's in these millions of objects. Now you write a SQL query, and it'll tell you exactly where to go. Uh-oh. Okay.
Hello. My name is Craig. I'm with Radiant Solutions. I had a question. Are you currently in the process of converting to cloud-optimized geotiffs with any of your current data sources? And what is the best way for someone to convert current data into optimized geotiffs?
So the Landsat data does get converted from just regular TIFFs, the TIFFs that USGS provides, into cloud-optimized geotiffs, and they use GDAL to do that. So GDAL is a very common open source library to do that. I don't remember the address right now. I think the GitHub repo is called Landsat-PDS. But is that right? Okay, so the code to do that is on GitHub. You go to the GitHub repo called Landsat-PDS. It's Planet Labs, just Planet now. They put that up there so you can see exactly how they do it. They've documented it.
Maybe just a comment to this. So for Sentinel-1, there are about 4 lines needed to convert with JDAL from the original Sentinel-1 to the cloud-optimized geotiff. So it's very simple. But anyway, my question is the following. So we build a business on the open data, and obviously we appreciate what you're doing. And but what I notice is that you have tens of thousands of customers in public service and only 59 open data sets. And obviously we would want more, right, so that we can build more business. And because this also helps Amazon, because building business brings revenue to you, I wonder whether you were thinking of some incentives for the providers to help them move the data to the cloud in the open data set way, kind of? Yeah.
I mean, I can say we're thinking about it for sure. It's, I mean, I think, like I said at the outset, what motivates us and what we get out of bed in the morning to do is to expand access to data, and part of that means getting more data. You know, I think we definitely we are greedy for data, and scaling that up and getting more data sets on there. I don't think it's going to be a matter of us just going out and grabbing stuff. We really need to enable the community to do it themselves. So we're looking at ways to do that. I can't share any details, but the answer is yes.
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 Any last questions? Yep.
Yeah, I have one. Do you have a figure of merit of how much access does a data set get? Say like 10% of the data set gets accessed every month or something similar, and what is that figure of merit for some of the most popular data sets?
That's a good question. So the answer is not no. And the challenge is the data sets are so different, right? So like that IRS data set is, it's 11 billion objects, but it's probably a couple hundred megabytes, and then Landsat is like a petabyte of data. So it's sort of hard to measure it by volume. And different types of data gets access in different ways. The big indicator that we look for is people that are building things on top of it. Yeah, so like tutorials and examples that's in the registry is like probably the big way that we measure success.
I got one last question in the back here.
Okay.
Keeping all the sort of the details short, because I know we're really short on time, do you guys have any solutions or best practices, or just sort of looking to the future things that you might be looking at for helping people to share data sets which would otherwise be sort of personally identifiable information? So being able to strip out the PII and saying, we're not going to tell you what the source is because, this is healthcare data, or this is education data, and we want people to be able to do analysis on it, maybe through some sort of encryption.
Yeah, I would say we have some data sets right now that aren't anonymized data sets, but they're controlled access data sets. So it'd be a kind of thing where you have to sign an agreement and be an accredited research institute or something like that to access and work with the data. Right now I don't know that we're hosting any data that's public that's anonymized exactly. We have talked to customers about that, and I think our guidance right now is using partner products and third-party tools to do that anonymization. If you have data like that, it'd be great to discuss.
All right. Thank you to our fabulous speakers, and thanks for everyone for attending. We've got a brief break coming up. Next, the last set of sessions begins at 3:05, and then don't forget to stick around for the awesome 4 p.m. Back to the Future party upstairs.
All right.
Hang in for another hour.
All right. Thanks, everybody.
Thanks, guys.